It's a great pleasure to introduce Aditi Kar from Royal Holloway College of University of London, who's going to talk to us about ping pong on cat-zero cube complexes.
Thank you for the invitation. I'm going to talk to you today about my joint work with Michah Sageev. So today let me say this. So let me, at the very beginning, say that the talk is about cat-zero cube complex, and I'm going to assume a basic knowledge of the structure of these things. And if you're really very worried about something I've said, just ask me. And so the ping pong lemma is a really it's an old thing now. It's more than 100 years since the first appearance, when Felix Klein was really studying Fuchsian groups, and he wanted to find free subgroups inside them. And of course, the major use comes later, much later, when Tietz, he does his Tietz alternative for linear groups. So today's underlying theme, in a sequence of two papers that we have been doing, is basically we're looking for these free subgroups and subgroups which look like basically free products inside. And we want to get to structural properties of groups acting on cat-zero cube complexes using these techniques. Right, so my plan today is to give you a very quick survey of what we know, and then focus on some techniques, because more than the main theorems, I think that some of the techniques are what you can take away and maybe use in your work. So let me start then with the Tietz alternative, and So what do we mean by the Tietz alternative? Let me just make a definition. So we say that a group G satisfies a Tietz alternative. So somehow there's a dichotomy in the behavior of subgroups. So it satisfies a Tietz alternative if for any subgroup that you give me inside G. Now for some people, you might limit to a collection of finitely generated subgroups, but here I'm just going to say if for any subgroup H, a subgroup of G, then either H is basically small, meaning amenable or virtually solvable, or else you can find it's large in the sense that you can find a copy of a non-abelian free group inside it. Right? Now, I think it's almost 20 years now, maybe, or roundabout then. We do know a Tietz alternative, and this is where sort of, let me start with that. So, the Tietz alternative, what happened? What is the story for groups acting on cat-zero cube complexes? So this is for so what happens? What do we know in this situation? We know basically, so this is a theorem due to Sageev and Danny Wise, and what they say, and let me be very specific on the on the ingredients, on the hypothesis. So let's suppose G is acting properly, so all stabilizers are finite, acting properly on a finite dimensional cat-zero cube complex. Now, if you just think about this, and then if you think about, so that's not doing very much. This is not a very strong hypothesis. Because, for instance, if you just take something like, right, you take, the sort of, and just sum up infinitely many copies of a finite group, of your favorite finite group, and you can make it act properly on some tree. Right, so that's not a very big hypothesis to put on, right? And I want to remove these possibilities. So it's acting on a cat-zero cube complex, and the right hypothesis turns out to be that there is a uniform bound there is a bound on the size of finite subgroups. Or if you like, you can say that every increasing chain, every chain of finite subgroups has to terminate, has to stabilize. Okay? And then you do have what you're looking for. Then G has a Tietz alternative. If H is a subgroup of G, then either. Now, when you have nice actions on cat-0 cube complexes, the virtually solvable, the subgroups in such groups are fairly limited. They're all virtually abelian. In fact, the dimension, the rank of such a subgroup is determined by the flat you have inside. And you can say then either H is finitely generated, virtually abelian, or it contains a copy of the free subgroup. Okay? So this is almost 20 years ago, and probably one of these sort of one of the first theorems in this theme. Now the proof does not use the ping-pong lemma, and I'm going to get to that, right? Yeah, I'll say a word about this. So Sageev and I, we were looking for generalizations of such sort of properties, and so the two things that we look at are, one is called property P naive, and the second one is uniform exponential growth. Right, so these two things now are sort of really different, probably. I need 2 talks to tell you enough about the two things. So, and I know that Michah has spoken about uniform exponential growth here. So I'm going to make a very brief account of this and then focus on stuff around property P naive. So let me make some definitions. So what is property P naive? This was introduced, right, let me give you a definition and then talk about some of the historical concepts. Okay, so a group G has P naive if. So you give me any finite collection inside G, and I'll remove the identity just for so it's a subset, and F is finite. Then, depending on the F you've given me, I can produce Y and G of infinite order in G, such that, right? Okay, so I'm going to take this Y and one of these elements, each of these elements here, and look at the subgroup. So for any F, X and F, I look at the subgroup generated by an X and Y, and this is as free as possible, meaning it's the free product, right? So if X is of infinite order, then you can just say this is F2. But notice it's very specific. These are the generators of your free subgroup, right? It's not X to the n which works. And it's very, it's a special definition. We know that it holds for some classes of groups, but yeah, the main group for which I think we don't know are the SLNZs. So I think this is still an open question. Does this have P naive? And the closest work that has been done is sort of several years ago, which are variations on P naive. But so let me make some historical background for this property. P naive was introduced by Becker, Cowling, and De La Harpe, I think. Okay, so they were studying what is called C-star simplicity. And I think I don't want to get into this, but this is a property. This is a very algebraic property. This is a very algebraic property, but this has to do with a group algebra which has an analytic flavor. namely the reduced C-star algebra of G. This is the reduced. Right, so now if you know about it, that's great, but if you don't know about it, I'm not going to define it, but you should just think analytic group algebra. And so anytime you have an algebra, you can ask yourself, does it have non-trivial ideals? And a group is C star simple, G is C star simple if if the reduced C star algebra has no non-trivial ideals, two-sided. And strangely enough, what they found was that this rather nice algebraic property implies C star simplicity, right? Okay, so P naive basically was a vehicle for establishing simplicity of the C star algebra. Okay, so yeah. So our main motivation was really because, proving P naive. C star simplicity was known for groups acting on irreducible cat-zero cube complexes. And I mean, this just puts it in.
It's automatically implied?
What?
It's automatically like.
No. This is theorem.
No, I mean it's theorem, but it's in general. The way you say it, it sounds like it was a tool to prove it, or that's really a theorem that P naive implies the simplicity of the C star algebra.
Yeah, well, this is one of the results in. So yeah, so maybe I should say theorem really. Becker, Cowling, Delaharp. This is that P. So should put it up there where I've written it. Yeah. You have to do some computation here with the elements. It's not. I mean, it's not. I'm not saying it's obvious.
No, but yeah. You wrote that this establishing. You mean it's really implies this?
Yeah. Okay. It's yeah.
Okay, good.
Yeah. Okay. I think that's a more without the fluff and. Right. Okay. So this is what we, this is. But our goal was not this. Our goal was really this, and something stronger. What?
It's not known if.
The C star simplicity is settled because there are other ways of getting there.
So it's known for us.
Yeah, but it's not, the P naive is not known. So you can get to, so I should say there are other ways of getting here. So there are other ways of getting here. I'll comment about this in a bit. But this, it hasn't been settled for S. Lindsay.
For general I run clavices, the simplicity is known?
I think so, yeah. Yeah. So at the time when they were working on this, they had other methods. And they do a lot of these lattices in that paper itself. And yeah, and then C star simplicity was studied, and people did it for hyperbolic groups and other things. But now I'll mention a result, more recent result, where they have other techniques for doing this as well. Okay, so where was I? So let me give you my bookkeeping theorem, and not all of this is. It's a nice way to put a lot of implications together, and this appears, I mean, this is for cat-zero cube complexes. So, and here I'm going to assume, suppose G is acting properly and co-compactly. And co-compactly on a finite dimensional cat-zero cube complex. The following are equivalent. So it really, I don't want to put. I'll put names with the implications. So the following are equivalent. One is the fact that G has P naive. 2 is the fact that G is C star simple. 3 is the fact that G is, let me write this and then tell you what this is ICC. 4, the amenable radical of G is trivial. And finally, did I give my complex a name? So the action of G is faithful, the G action is faithful. So there's no element which fixes everything, and X is not Euclidean. So 1 implies 2 implies 3 implies 4 really is well known, and basically this is BCH. Okay, and 4 and 5, the equivalent of 4 and 5 comes out of, we do write this out in our paper, but it really comes out of stuff you know about CAD0 geometry. And then 5 implies 1 is one of our our theorem. Okay, so what should so P naive, I've told you, C star simplicity, G is ICC. ICC stands for infinite conjugacy classes. And it means that if you take any element which is not the identity in your group, its conjugacy class is going to be infinite. And when you think about it, you can already see, for instance, groups like this will not have center. But more generally, there's going to be no amenable radical, right? There's going to be no normal subgroup which is amenable. Now, going from here to here is, yeah, okay. You need to argue group theoretically, but it's not hard, and they do that already, and they write it up in the paper I've just mentioned. Okay, and here you see what I like about this is algebraic properties are controlling analytic properties, and not only that, they're controlling some of the geometric properties. And here what you see is X is not Euclidean, meaning that there's no, you split it up into its, you split up X into as much as you can as a product, right? None of these are going to be Euclidean factors. Okay? So you're not going to see Rn sitting there with CAD0 geometry in any of these factors. That's what it means that, any such thing is going to contribute some sort of amenable radical. Okay, so that's the bookkeeping theorem, but but this is not the best we can do, actually, because there has been recent results due to, so even though this paper is not really about C star simplicity, let me say this, there has been recent work of Boyer, Kalankar, Kennedy, and Ozawa. And I think this is in the last 2 years. Shall I say 2016? Or maybe 15? I don't know. But it's fairly recent. And using that, actually, the best you can do for CAD0 cube complexes and C star simplicity is the following. You have the same hypothesis as you have for the Tietz alternative. So G is acting properly on a finite dimensional CAD0 cube complex, and there is a bound on the size of finite subgroups. And then, so hypothesis as in Tietz alternative. And then you can say that G is C star simple if and only if the amenable radical is trivial. And this is really the optimal theorem, because I should mention here that Adrian has very nice, Labudek has very nice examples where, if you don't have this condition you don't have the same set of hypotheses, you can get, sort of things which violate the theorem. Okay, so that's the story in terms of C star simplicity. But we proved something which was a bit more general than that. So main theorem. So here, my x is going to be, G is acting on x, cat0 cube complex, x is finite dimensional, irreducible, so it doesn't split into factors, and non-Euclidean, meaning it's not going to be and then you've got, so the beautiful thing about cat0 geometry is that there are hyperplanes, and hyperplanes cut up your space into, partition your space, right? So we have this notion of being, of a subgroup being inessential. So a subgroup is initial, so now I need to erase something. So here's my cat0 cube complex, and you've given me a subgroup A, and basically I can look at the translates of a particular vertex by this subgroup, right? Now that is not going to spill over into the entire space, meaning that there's going to be a hyperplane H, and the entire orbit is going to be on one side, and this is the notion of a subgroup being inessential. Okay, so what we basically prove here is the following. So if A1, right, we have got a finite collection of simultaneously inessential subgroups. Okay, this means that you can do this for all of them. Then there exists a Y in G such that, right, and this is for each I you've got a free product. Okay, so right, so what's a typical example of an inessential subgroup, right? You can take hyperplane stabilizers, right? If your space is not just, is not just kind of, within bounded distance from the hyperplane, so it's an essential space. Then once you have one hyperplane, you can find a wealth of other hyperplanes which do not intersect that one, and you will be, you can come up with examples where hyperplane stabilizer can be an inessential subgroup, right? Okay.
Could you just clarify when you said the hypothesis for the Briard, etc.?
No, I'm sorry.
You said the hypothesis as in the Titzel table. Do you mean? Are we talking about that Titzel
Maybe
table?
I went through that really quickly. So let me step back. So there are recent results of these four authors, using which right. So I really have put my. So I think I should spend a bit more time on this. So what's going on here? These traditional, since the work of BCH, there have been developments, and this recent development really brings up new techniques for finding, for establishing C star simplicity. And some of these new techniques are in this paper, and this is it uses the action of the group on a boundary, and basically the action has to be of a certain nice nature, has certain adjectives. In particular, being what is called topologically free. So you have a nice minimal action, so on and so forth. And using that, you can, with the same hypothesis as in the Tietz alternative, for groups acting on cat0 cube complexes, you can establish this equivalence. Yeah, thank you. Yeah, I should have taken more time on this. Right. So I am going to give you the G boundary actually if I have time, given how I'm going. Okay. So
another question. simultaneously in essential subgroups.
Meaning that you can.
So what should I have in mind? Stabilizer of disjoint hyperplanes?
Yes, you can do that. I don't think they have to be disjoint. You can just have. You've got your cat-0 cube complexes, and you've got hyperplanes, and
But stabilizers of disjoint hyperplane is good enough.
yeah.
Just to have a picture in mind. Thanks.
Yeah. Yeah, just take spacing triples, right? That's probably what you. Yeah. Okay, so having said that, any other questions? Anything that I haven't clarified? Okay, so my plan was to really show you how this ping pong works in this particular case, at least with one subgroup. But I'm not sure that this is going to actually work out in the sense of time. Now, what should I say about uniform exponential growth? I mean, I don't think I should try to define it, but essentially, you can already see from the Tietz alternative that you've got free subgroups floating around, and the group is going to have exponential growth. Uniform exponential growth was defined by Gromov, and this is basically a property where you can very quickly find this this exponential growth happens in a very, very controlled fashion. And maybe I should make a bogus definition actually. Should really. So a group G has uniform exponential growth if there exists a constant C greater than 0. So this is a uniform constant depending only on the group, such that for any generating set, right, for any S, you have the following. You look inside the ball of radius C inside inside your Cayley graph, right? And inside this ball of radius C, you're going to be able to find two words U and V in the generating set, right? Such that there exists U and V inside this ball, such that they generate your free subgroup. Okay, so it's exponential growth in a very controlled fashion. You can, and yeah. So yeah, this is ongoing work, and we do uniform exponential growth for cat0 cube complex groups, but only for 2 dimension. And it's a very uniform, right? This constant C is very uniform. So let me just take 2 minutes to write down the theorem. Now, torsion really is disturbing. We are not able to deal with torsion just yet. And so what's going on here? Suppose G acts freely on a cat0 cube complex. Actually, I need to give my. So there exists a constant C. I know what the constant is. Suppose G acts freely on a square complex. Then, for any generating set, for G, there exists U and V, right? The maximum length is at most something like 10. Right, such that the subgroup generated by U and V is F2. Okay, the constant works for any group acting on a freely on a. So it's a very uniform constant, but the price we pay is that we still have 3 here and square complex here, right? And this okay, so I've given you 3 basically results. One is the Tietze alternative, one is this, and the other one is this main theorem from another paper at Michah. And they really have different flavors in terms of how you get to these 3 subgroups. The Tietze alternative, the proof is really non-constructive, but it is a beautiful application of 2 results of in this area. Yeah, it's a wonderful paper that fits into, I think, 2.5 pages or something like that. And the proof really uses Sageev's thesis, so which gives you a control of what are called codimension 1 subgroups, so stabilizers of hyperplanes, which allow you to get to amalgamated free products and therefore to free subgroups. And the other one is Dunwoody-Swenson.
Oh, it's an O. The last one's an O.
I was right, wasn't I?
Yeah.
Right, never hesitate. Okay, Dunwoody-Swenson, algebraic torus theorem. It's been a while since I algebraic torus theorem. Okay, it's a beautiful application of these 2 theorems. And it's completely non-constructive. And you might ask me, okay, we know the Tietze alternative. Why can't we easily do uniform exponential growth or something like this, right? Here, if you think about it, so it's a non-constructive proof for the ping pong. You neither need the table nor the partners, right? It tells you that they exist. In this particular theorem, you've got a willing player, but you have to find the table and the partner, right? In the uniform exponential growth, you have to very quickly find the partners, which can be very difficult in life sometimes, right? As we know. So they're all different types of results, requiring different degrees of detail and technical sort of ingenuity, let's say. And so Michah's already explained this, I believe, sometime in this semester. So let me say what techniques go into this, because I very much like one of the ingredients, and I want to tell you how this, and I think you can probably, it's possible that this is something that you could use, if you will. Right, so should I state the ping pong lemma? You think? No. Maybe. So what's going on in the ping pong lemma? Wait, the thing about using a ping pong lemma is that everybody has their favorite version, right? And in fact, I should say here we do semi-groups, and even though I didn't say that, but so the ping pong lemma, the version that I want to use, is going to say the following. So here there's no metric. So you have a group acting on a set X, and you're given 2 subgroups H and K, right? That is an H and K, subgroups of G, right? And suppose now, so here's the picture, right? You've got your set, and you can find U and V. Suppose there exist U and V disjoint subsets of X such that what happens is H, right, carries all of U into V, and K carries the other one, right? H and K basically exchange U and V such that, so I'm going to write it like this: U, V, all of it goes inside V, and H, U, all of it goes inside U, right? Then you have a free product. Okay, so this is what I mean by the table. You need the two sides, And these are the partners, U, H, and K, the ones which exchange U and V, right? So in this particular theorem, you've got one of the partners, you need to find Y. And you need to find Y which works for all those subgroups that you started with. So essentially the proof goes through finding these U's and V's, and to do this we use a particular boundary. And I think somehow sequely I just want to tell you about the boundary because it has some beautiful structure from the CAD0 geometry. Yeah, okay, so, and this is the boundary of strongly separated ultrafilters. Okay, so this is the, the boundary I mentioned earlier that, that can go into as a, that allows you to satisfy this hypothesis of the work for C star simplicity. But what is it? So I need to work step by step. Now, what happens inside? So you've got X as your CAD0 cube complex. And, right, so there's the entire language of hyperplanes which right? Now, so here my X is going to be irreducible, essential, and finite dimensional. And anytime you've got these irreducible CAD0 cube complexes, you have a wealth of hyperplanes which do not intersect, right? So what is the intuition that you must have, right? So yeah, so they have a wealth of non-intersecting hyperplanes, and this is the geometry that this boundary is somehow going to capture. Okay, so first of all, what's an ultrafilter? This is really a sort of a CAD0 cube complex version of the ultrafilters we know from logic, and so your hyperplane cuts the space into two parts, H complement and H, right? These are the half spaces, right? Each hyperplane gives you two half spaces, and so my curly H is going to be the collection of all half spaces, right? And an ultrafilter is basically on H is a choice. You make a choice of which side you want to be on, right? So alpha is an ultrafilter on H if. So there's the choice property, meaning that for each half space, right, either, wondering if I should put H hat there, but for basically either H is in alpha or H complement is in alpha, right? So you're thinking that this is an ultrafilter. So alpha, you're really thinking alpha is something contained inside the power set of H, right? It's a choice of half spaces that you're going to make, and it's going to choose. So you choose one side for each, and then there's consistency.
You say either or the other, you mean exactly one.
Yeah, exactly one. Yeah, exactly one. And consistency, meaning that if you've got one contained in the other, right? So if H is contained in, how did I do it, K, and you've already picked H, then K must already be in there, right?
So this is just equivalent to the half spaces intersecting always?
Which one?
The second condition is just equivalent to any two of these half spaces having non-empty intersection, right?
Mm-hmm. Right, so okay, so I've got my collection of ultrafilters. So one of the examples that you can think of, now how much, so a typical example is when you've chosen a vertex inside X, and alpha is the one which chooses, you know, always the half space that contains the vertex, right? These are the standard examples. Okay, but there are others. There are others which do not contain, you know, which don't correspond to these, and they don't also need to terminate. You can have these hyperplanes which have, you know, which are heading off to infinity, right? And in general, boundaries pick up these ones, which these in some sense these terminating ultrafilters. So the boundary of strongly separated ultrafilters. So I now need to tell you that two hyperplanes are strongly separated if. So the picture you have is the following. Here's your space, and you've got two hyperplanes, h hat and k hat. They don't intersect, but not only that, anything that intersects h does not intersect k, and vice versa. Anything which intersects k is not going to come and intersect h, right? So if two hyperplanes h hat, k hat are strongly separated if no hyperplane intersecting one of them may intersect the other. Right? Okay, so you hear a lot the fact that cat-zero cube complexes are generalizations of trees. And this is one of the situations where this intuition really is being, you know, fruitfully sort of extended. And because, for instance, if you just think about a tree, right? Right? Hyperplanes correspond to midpoints of edges. And really, you can see that, you know, they're basically all strongly separated. Right? Unless, yeah. Okay? And, yeah. So it's a very tree-like sort of behavior that you're picking up inside your cat-zero cube complex. Now, a very beautiful fact, and this I haven't got time to explain to you, but comes out of the work of Sageev and Kapras, is the fact that you've got, you know, there are many, many strongly separated hyperplanes that you can find in an irreducible cat-zero cube complex, and basically that allows us to define this boundary. So, in fact, if your complex is irreducible, right? In this tree picture, if you think about an infinite tree, right? You take this edge, cuts your tree up into bits, right? And that's one hyperplane. But you can find another hyperplane which is contained inside, right, half space which is contained inside the one you first thought of, which is also strongly, you know, corresponding to two, right? Okay, let me write this down. So, there are many strongly separated hyperplanes. So in fact, so this I should say, right, if your X is irreducible and then inside a half space H corresponding to H hat, that there always exists, you know, you can find K hat such that, so here's your H hat, you can find k hat inside H such that k hat, H hat are strongly separated. And the beautiful fact of life is that you can build these chains. You can find chains H1, H2, H3, all going off like that, such that each is strongly separated with the previous one. So you can find chains of half spaces such that HI plus 1 hat and HI are strongly separated. So they all have this very, very specific tree-like non-intersecting property with each other. Okay, so the strongly separated ultrafilters basically correspond to these chains. So these chains define the strongly separated ultrafilters. So there's something to be proved here. I've been a bit vague, but essentially you're making this choice according to this chain. You're choosing the half spaces. There are very few intersections here. If you've got any hyperplane and it crosses one of these, it's not going to cross any of the others. So it gives you a very, very precise way of defining your ultrafilters. And these are the ultrafilters that you pick up in this boundary. Okay? For a tree, this is the best possible scenario. These are the boundaries that you already know and are familiar with, like the roller boundary. But for other spaces, if you throw in sort of flats, you're going to get sort of maybe, potentially smaller bits of the boundary. So the proof really, takes this boundary and studies the action on it. And
So this boundary is the roller boundary, but you're only including those ultrafilters that have this nesting sequence?
you need to close it up, otherwise it's not going to be a compact space. But the building blocks are these strongly, so you take the collection of all strongly separated ultrafilters, and then you take the closure inside the roller boundary, and that's your compact space.
Okay.
So the strategy of the proof then is to study the action of G on what we call S of X, the strongly separated, the boundary. Okay, so let me just mention 3 properties instead of going into more details of the proof. The 3 properties which I think are interesting and probably of use to people. The action is what is called topologically free, and I haven't got time to talk topologically free. I haven't got time to define this, but you should just check the paper. The second one is basically, so anytime inside a cat-0 cube complex, if I give you 3 vertices, there's a notion of a median, right? There's the notion of, how does it go? Something, I've got this too close here. Suppose you've got that one, right? So you can, for ultrafilters as well, even though these points are on the boundary, you have a notion of median. So you've got alpha, beta, and gamma, and you can do a median for 3 of these. And it turns out if alpha, beta, gamma are these strongly separated guys, strongly separated ultrafilters, then the median is actually a vertex inside. Okay, this is an interesting property. You can ask yourself, for instance, I had the action of the group, And suppose there's an element of infinite order. How many of these can be fixed by an infinite order element? And you can see that only 2 of them can be, because as soon as you have 3, you're going to have a vertex which is going to be fixed by that infinite order element. And if your action is proper, you can't have that, right? So I think this is a property which can be sort of used in other scenarios. And the third one, which really goes into 1, is the following. If you have any element G, doesn't matter whether it's hyperbolic or elliptic, then you look at the fixed set of G inside the boundary. This will have empty interior. Okay, and in particular, I mean, this is a bit more special than that. There's going to be no half space that can be completely fixed by such a sort of, okay, right? The limit set cannot be fixed by the, okay. So the proof essentially uses properties like that to find the ping pong sort of arrangements. So what should I say now? That could be a bit, right? So to finish, you can use this boundary to show, right? So what did we have? We had a collection of these finitely many inessential subgroups. So, right? So there's some hyperplane H hat and some vertex V whose orbit you're tracking. So A1 of V, A2 of V, so on and so forth, right? And you can use this to show that there exists some other hyperplane, K. It is actually strongly separated from this H you first thought of, such that A of K, so this is your half space K, and that's your hyperplane H hat. And every element of these subgroups that you picked up is going to actually take you outside, right? It's going to, so anything from here is going to take you out, right? So you can see here, U and V have to be disjoint, and this is the first step towards achieving that. You can pick out a half space which gets shifted outside of itself by each of the elements, right? So K is moved outside of itself by each A in AI. And that's really the start of the ping pong. And then you have to do some more magic to get the ping pong partners and the rest of the, the rest of the arrangement. But I mean, that's basically, so my plan today, my intention was to really explain the boundary to you and show that, this is sort of the structural part of the paper. So I've mainly, so my last comment here really is that I've concentrated on the irreducible case, but it works for products as well. You can do P9 for products, but basically lattices. So for instance, Pierre-Emmanuel talked about what the Berger-Moses groups, or BMW groups as he called them, and yeah, you can do P9, for instance, for groups like that using these techniques. So products also work, even though I haven't sort of touched on them. Okay, thank you.
Questions?
I mean, some of these methods seems to, maybe they have a chance to work for the mapping class group. Is there anything in this direction that was done?
So uniform exponential growth is known for mapping class groups, and yeah, this is a paper by.
Well, it's kind of obvious because it's surjective and it's PNZ, which has uniform exponential growth. Uniform exponential growth for mapping class group follows that it's surjective some linear
Yes.
groups that
So
have the
yes. So
What if you are in the kernel? If the elements are in the kernel, you get nothing.
So let me say two things. Yes, there is a map onto SP which helps you out to find lots of free subgroups. But now if you're looking also for free subgroups inside subgroups of the mapping class group, there is work by, I'm not going to be able to spell this name, but is John here? No. Yes. So there's work by Johanna Mangerhas. She does uniform exponential growth actually for all subgroups of the mapping class group. So she calls it uniform exponential growth, and this is I. Mapping class group C star simplicity is known, and I want to say it's Martin. Is that you? Yeah.
Me and Pierre Delahaye.
Pierre Delahaye. So.
But this is for the full group, right?
P naive for the full group, yeah. C star simplicity for the full group, yeah. So this is uniform exponential growth. Brighton plus Delahaye. So this is C star simplicity. Yes, it is very, yeah, anywhere where you have some sort of, I don't know, I want to say convergent style action, you can do this, play these kind of games. And
This is not through the P naive property.
what?
This is proved.
No, this is not use, it does not use P naive, right?
P naive
But
is
is
not,
P
no?
naive known? Probably not, if it's not.
It is by about.
Oh yes, François, I'm very sorry. Damn. So since my paper with Michah, P naive has been proved for acylindrically hyperbolic groups. Acylindrically hyperbolic groups. And it so mapping class group, you can do P naive, that's right. Sorry, I really meant to mention you, and I don't know how I forgot. I should sometimes look at my notes. Yeah.
I suppose that naturally leads to the question, but I don't know if you should answer it or Francois should answer it, whether uniform exponential growth for acylindrically hyperbolic groups is...
No, this is a hard thing, and I have to tell you the difficulty, one of the difficulties is actually to deal with elliptic elements. So if you think about, and this is also our difficulty in Cat0 cube complexes currently, so for instance, if you think about how one would do uniform exponential growth for hyperbolic groups, you have to address the question, actually this is the title of Emmanuel's talk, how quickly can you get to a hyperbolic element? So one of the steps in the proof for the hyperbolic group is the fact that you can find a constant which depends probably on delta, so that if you look outside a ball of radius, that function, I'll call it C delta, right? So yeah, if you leave this, you're going to be able to find a non-torsion element pretty quickly, right? So this is the kind of thing you need to do. How quickly can you, so you can play ping pong if you have the players. And in this situation, one of the difficulties is as soon as you have torsion elements in your group, how quickly can you get to a hyperbolic element? And I think in the acylindrically hyperbolic group, right, infinite order elements can also be elliptic, right? I mean, it's not. So this is an essential difficulty. Yeah.
Any other questions? Let's thank Aditi again.